All right, guys, this is our last lesson for this week. It is on friction, and away we go. So, well, actually, going back to here, when you're looking at a typical free body diagram, you'll notice, well, sometimes we have this frictional force, which resists the motion of the object relative to a surface. And we've got gravity down, and you may remember I often say that the ground force is up, resisting or opposing the force of gravity. But really what that is it's the normal force. Fn is the normal force. The word normal actually means perpendicular. And in this case, it's perpendicular to a surface. So if you have a box or a car or anything on the ground, then there exists a normal force that is up. If you're on a ramp or something, then the normal force will be perpendicular to that ramp. Again, the word normal implies perpendicular. Even if you're pushing something up against a wall, the normal force will come out and be perpendicular to that wall. All right. The most common situation is this one here where it opposes gravity. I've got a bunch of things sitting on my desk right now. Gravity's trying to pull them down through the desk, but there exists a normal force perpendicular to the desk that holds those objects up. So the force of friction, F subscript F, is a force that exists between two objects. It opposes the direction of motion. So we've got two types of friction: static friction, which sometimes is denoted Fs. I usually just call them both FF, static friction, and kinetic friction, but it doesn't matter. The force that prevents a stationary object from moving. So like if you're trying to push a refrigerator, then you're going to be pushing with, let's say, some sort of applied force. And if it doesn't move, then you've got this static friction that's holding it back. Static friction holding it back. And I'm sure there's a diagram or something to pop up here. Maybe not. Kinetic friction, FK, or again, I usually just call them both FF, is the force of friction that opposes the motion of a moving object. So, like if you're sliding a trunk or skating or letting a car come to a rolling stop, there's going to be friction. So in this case, there's already a velocity. So in some cases, there's no forward force. All there is a force of friction backwards. We had a question like that. When I was taking up those questions, there was a puck sliding along the ice towards the end of those questions, and there was only a force of friction on the object. And of course, there's still the normal force, and there's gravity. And since I don't see a diagram over here, I'll put one in. So you've got some applied force trying to push the thing forwards. You've got friction opposing it, and you've still got gravity. You've still got the normal force. Again, pause these videos if I'm moving too quickly. The coefficient of friction is a ratio, that means fraction, of the frictional force to the normal force for a certain pair of substances. And its symbol is mu. It's found by going force of friction divided by the normal force. What would the units be on mu? Well, if you're going newtons divided by newtons, there will be no units on the coefficient of friction. If you need a triangle to help you along with this, there's your mu, here's your friction on top, and here's your normal force down here. In most cases, you're just going to say that the normal force equals the force of gravity. Like I said, in most cases, you've got an object, you've got gravity down, and you've got the normal force up. So they always balance each other. They're equal to each other. And for the most part, I'm going to stick to situations like that where you can say that normal force equals gravity. I'll let you know when we're moving away from that. So my symbols here have taken a little bit of playing some tricks on me here. But if you have a small mu, that means you have very little friction for a certain weight. And for slippery surfaces, if you have a large mu, Let me just get some of these drawings out of the way for you. A large mu means you have a high friction for a certain weight. Anything that is grippy is going to have a high mu. Now, see how they drew that mu? It's a U with a funny tail. Well, it's. I guess, and I'm even using the term mu. Let me try and draw these a little better. It's a U with a tail there on the left, and it's the Greek symbol mu. It's pronounced MUE. That's how you'd say it, is mu. And it just stands for the coefficient of friction. Instead of saying coefficient of friction all the time, I often just say mu, find mu, calculate mu. Here's a bunch of mu's for both kinetic friction and static friction. I don't know whether I need to highlight any of this. For those people that are hockey players, steel on ice, a very low coefficient of friction. Rubber on asphalt has a fairly high coefficient of friction. The lowest one on here, I'm just trying to look. Cartilage on synovial fluid. That's where our joints are able to rub so effortlessly across each other. And I mean, you can come back to this if you need any of these mu's, but I don't think we really need them. It's a list that's from a textbook, an old physics textbook, and it just lists a whole bunch of coefficients of friction, both static and kinetic. I'm not going to worry about this slide right now, so don't even write this one down. How can we change friction? Well, here's the formula. That's just a rearranged version of mu equals friction over normal force, the one from the other slide. And one way is to change the coefficient. Well, how can we change the coefficient of friction? Well, we can change it by altering the surfaces that are in contact. A way that you can do that is putting oil in an engine, right? That's going to change the surfaces, change mu. Rather than steel on steel, you've got oil in between. Putting sand on ice changes the mu. Instead of ice, you're on sand and ice. Changes the mu. The second way you can change friction is to change the weight. Change Fn. Increasing the weight will increase friction. And if any of you drive pickup trucks usually, unless you have them in four-wheel drive, are going to be rear-wheel drive, and the least weight in a pickup truck is on that back axle. So you can lose grip. You can have too low a friction to be running in the winter on ice. So you put sandbags in the back of the pickup. It increases the weight, which increases the force of friction. Because friction equals mu times Fn. I'm a little embarrassed about my mu symbols. I got to take my time. It's a nice tail and then a U like that. That's what I was going for there. So here's a couple of examples. It takes a force of 548 newtons just to get a box with a mass of 128 kilograms moving to determine the coefficient of static friction. So let me draw that box, and I'm going to write 120 kilograms in there. All right. It says it takes a force of 548 newtons to get it going. We've got some gravity here. We've got a normal force here. So what can we find with that mass? We can find the force of gravity. And I would encourage you to solve these problems using the diagram, using the free body diagram. This is totally fine. Go Fg equals mg, which is 120 kilograms times 9.81. Let's assume this is on Earth. So on my calculator, I go 120.981 is equal to 1177 newtons. So what would you think that the normal force is equal to? How are we going to calculate the normal force? Well, that's easy, because gravity and the normal force have to balance each other out here. I don't think that the box is going to crash through the floor or start flying, so these have to equal each other. So if gravity is 1177, then the normal force is also 1177. So what does it want? It wants the coefficient of static friction. I'm going to do that off to the side here. I'm going to try and make a nice mu. That one doesn't look too bad. is equal to friction divided by the normal force. All right, well, now we know the normal force is 1177. We don't yet know friction. It says it's pushing with 548, but if it takes it 548 newtons just to get it moving, that means that friction was 548 newtons also. If that's how much force it takes to start it moving, then that's what friction was. So I go 548 newtons here. Notice again the newtons cancel out. There's no units on our mu, and I go 548 divided by 1177, and I get 0.47 for the coefficient of friction. That is how you tackle a problem like this. Example number 2, it takes 254 newtons to keep a cart with that weight moving at a constant speed. Determine the coefficient of kinetic friction. Some people get thrown by the word kinetic, but it's the same thing, calculating mu. Let's draw the free body diagram again. We have gravity, we have the normal force, we have 254 newtons pushing forward. We know that there's some friction backwards, otherwise how can we calculate mu? Start with gravity. Well, it equals mg, but I'm just noticing in this case it tells you the weight. It doesn't say the mass and we have to calculate the weight. It says it weighs, and that's gravity, 520 newtons. What's that mean the normal force is? 520 newtons. If it's traveling at a constant speed, and that's why I underlined that term, that means that the forces must all be balanced. And that makes it a lot like the first problem, because if 254 newtons are forwards and we're moving at a constant speed, then there has to be 254 newtons backwards. All right, now we're ready to finish it. I'll take my time, draw a nice mu. It's equal to friction divided by the normal force. And now we have those things. It's 520. No, it is 254 newtons divided by 520 newtons. 254 divided by 520 equals 0.49. I don't know if you noticed when we were looking at those coefficients of friction, but pretty much the highest coefficient is 1, right around 1. Something that's real grippy has a coefficient of friction of 1. I think I saw maybe a 1.1 in there somewhere. But that's a really high coefficient of friction. If you're calculating these and you get like a 3 for coefficient of friction, either you did it wrong or I created the question incorrectly. Anyways, example 3. 2,500 kilogram truck tries to stop in the ice. There's a coefficient of friction of 0.0047. What force of friction is available for stopping? So now it wants me to calculate the force of friction. Force of friction equals mu times the normal force. All right, good. We have mu, 0.0047. We don't have the normal force. We're going to have to figure that out. We've got 2,500 kilograms, gravity down, normal force up, and friction backwards. Not that I need most of these things, I just need to figure out what the normal force is so I can finish this problem. It's going to be equal to the force of gravity, which is 2,500 times 9.81. Remember, mass times g. 2,500 9.81 is 24525 newtons. That means that's the same up here, 24525 newtons. And that's going to go here, 24525 newtons, 0.0047, 24525. And this gives me, if I'm rounding it to, let's say, 2 digits, it's going to be about 120 newtons. My calculator actually gave me 115.2675, and I have to 2 digits rounded it to 120 newtons. It's about as, well, I shouldn't say that. This right here, if I was going to give you the real in-class test, this This was supposed to be the last question on the test, the hard question on the test. Okay, this one was the big one on the end of the test. If you didn't know what you're doing, you're definitely getting this one wrong. So try and follow it. On the work I assigned today, there's another one just like it, and I guarantee you, on whatever assessment I come up with for this chapter, it'll be on there as well. So it says a 9.5 kilogram box has an applied force of 11 newtons on it. Gives me a coefficient of friction. A says calculate the force of friction. B says draw the free body diagram. Now, I don't remember when I came up with this slideshow, but I always like to draw the free body diagram first. So I'm going to start by doing that right over here. So I'm going to answer B first. 9.5 kilograms. We've got gravity. We've got 11 newtons forwards. The normal force will be up. And we've got some force of friction backwards. Now I'm going to calculate the force of friction. Now to do that, I have to do a bunch of things. I need the weight, first of all, which will be the mass, 9.5 kilograms, times 9.81 newtons per kilogram. So I go 9.5 times 9.81, and I got 93 newtons. That means the normal force will be 93 newtons. Now over here with friction, it's equal to mu times the normal force. Now that we know the normal force and the question gave me mu, I can go 0.25 for mu times 93 newtons. 0.25 times 93 is 23 newtons. I've rounded my answers here, but that right there is the answer to A. So now I've done A, I've drawn the free body diagram, I've used the free body diagram to get a bunch of different things. So let's now do C. C says find the net force. Now some of you will think, well, I know how to do that. You go mass times acceleration, but we don't know the acceleration. As a matter of fact, the last part of the problem is it asks for acceleration. So the net force is just going to be the sum of the forces on the object. So I've got 93 up and 93 down. Well, they just cancel each other out, the normal force and gravity. I've got 11 newtons forwards and 23 backwards. So I'm going to go 11 newtons forwards minus 23 newtons backwards. And you can do this in your head or on your calculator if you want, but I'm just writing out what I'm doing. 11 minus 23 gives me negative 12 newtons. All that means is 12 newtons to the left, backwards 12 newtons. So that's that. That one's done. You could have also expressed that as 12 newtons left. And then finally, D, find the acceleration. Remember, Newton's second law is F net over m. A equals F net over m. Now we know the net force is negative 12 newtons, and we know the mass from the original data in the problem. So it's going to just be negative 12 divided by 9.5, which gives me 1.3, negative 1.3 meters per second squared, or you could have said newtons per kilogram if you prefer that unit. So that's everything. Like, that really does cover a lot. Like, I could even argue this could be the only question on your next assessment, because you have to do it all. You had to calculate gravity. You had to find the normal force. You had to calculate friction. You had to find the net force. And then you had to use Newton's second law to find the acceleration of the object. Like, it covers all the bases, which is why it's usually the last and most tricky question on the test. You have to understand all of it to do this problem. So I posted work on Classroom, and there's two worksheets there. There should be one on gravity and one on friction. All right. You can print those off, complete them by hand, and then send back pictures. I am going to grade this. It'll be the only assignment that I grade in this chapter, so make sure you do turn it in. Or if you don't have access to a printer, your other options would be, you could use the PDF and just annotate right on it. Make sure you do full solutions. And then finally, you could just look at it online, do the solutions on paper, and submit that, right? You're going to be taking pictures with your phone or your tablet, and you're going to be submitting the pictures of your answers online for the most part. All right. So that's all I really need you to do this week. It's a little lighter than last week. I came out guns a-blazing last week. But we can take it a little slower this week. And even if you have questions you got to finish from last week, go ahead and finish those. Keep the questions coming. Email me and I'll respond to you as quickly as I can. Okay. That's it for now.